Alright, so for this particular video, there are a few multiple choice questions on harmonics or simple harmonics for you to follow if you need to. Here's the first one. It says a spring of force constant K is stretched a certain distance. It never gave it what the distance is. It said it takes twice as much work to stretch a second spring by half this distance. Okay, and it wants to find the spring constant for the second spring. Alright, so to do this, essentially, all you have to recognize is that work that needs to be applied to stretch a spring will be stored in the form of potential energy in the spring. So here I made the statement: the work done by the applied force in order to stretch a spring or compress it will be stored in the spring in the form of potential energy. All right, so we know from our definitions that the function for PE spring max is simply 1/2 kx squared, but x got replaced with a for the amplitude because that's the maximum distance that a spring is compressed or stretched. Okay, so here really I'm just going to apply this function twice. I'm going to apply this function for the first scenario. With the spring for the first scenario, it's just k. It said it stretched a certain distance. Again, it never said what the variable is, so I'm just going to stick with the letter here, a, for amplitude. However far you decide to stretch it, or the moment you stop stretching it, that distance is called the amplitude. And then I'm just going to apply it for a second time. On the right side here, well, the statement says that it takes twice as much work. So instead of W, I'm just going to multiply W by 2, whatever W is. And it says to stretch the second spring by half this distance. So if the first spring is stretched by capital A, well, the second spring says it's half. So I'm just going to say A divided by 2. And then all that will be squared outside the, or all the stuff inside the parentheses will be squared by the exponent outside there. Okay. So here I'm just going to go ahead and distribute the exponent to A and the 2 in the denominator. So it'll be A squared divided by 4. Again, 2 squared is 4. So from here, as you can see, you can just really simplify this function down, so it's not too bad. You have a W expression on the left side, you have a W expression on the right side, so hopefully you recognize just to do a substitution here. All right, so I'm just going to simplify the right side. 1/2 times 1/4 is 1/8. So again, the numerator here has a 1. 1 times 1 is just 1, and then 2 times 4 is 8. So I'm going to clean this up a little bit. K2 gets carried down. The A squared gets carried down. On the left side, I haven't done anything. So here, if you've done enough of these ratio problems, I'm just going to go ahead and substitute out W, or the net work here, using the left statement. So the problem initially said that you do a certain amount of work to stretch the spring a certain amount of distance. Well, here you have a sigma W term, so I'm just going to replace that. I'm going to keep the 2 in front. I'm going to carry that down. So instead of saying net work, I'm just going to replace it with 1/2 Ka squared, which was the initial given condition. And now on the right side, everything stays the same. So really you're done here except for just canceling out some stuff and just cleaning it up. On the left side, there's a 2 outside the parentheses. That's going to cancel with the 2 on the bottom. And then you see both sides has an A square, so I'm going to go ahead and cancel that out as well. So as you can see, the only thing really left here on the left side is just K, right? So 2 over 2 is 1. 1 times 1 is 1. And then A squared is already canceled out, so the only thing left is K. On the right side, the only thing left is 1/8 K2. So to solve for K2, I'm just going to multiply both sides by 8, so the answer would just be 8K, and that matches with choice D. Okay. All right, let's move on to the next one. Here in the next one, it says a particle oscillates in some harmonic motion with some period t, and it says at times equal to 0, the particle has its maximum displacement, which graph shows the kinetic energy as a function of time. So here I provided a diagram for you. It says here at times equal to 0, it has a maximum displacement. So when it says maximum displacement, you can either be on the extreme far left or extreme far right. So here I just have it extreme left here because it never said whether it's positive displacement or negative displacement. Okay. So here you're just trying to find a KE versus time graph. So I like to point this out. From negative A to 0, that's only a quarter of a period. And then from negative A all the way to positive A, that is a half a cycle, because for a cycle to complete, you have to start there, go to 0, from 0 keep going to the right, that's a half a cycle, and then from the positive amplitude all the way back to where you started, that completes the cycle. Okay, so I think it's important for you to break down these time intervals into 4 pieces. So from negative A to 0, that's a fourth. From 0 to positive A, that's another fourth. And then positive A back to 0, that's another fourth. And then from 0 back to negative A, that's another fourth. So therefore, it would make a whole cycle. Now, that's important in this graph because Okay, you're given here kinetic energy as a function of time, and all the capital T's are given to you here in these graphs. So I'm just going to go ahead and cross out a few things, or a couple of things here, just based on what it cannot be. Okay, energy is a scalar quantity. When you're given energy as a function of time for these harmonics, that cannot dip below the t-axis. A scalar quantity must remain above the t-axis. So I'm going to cross out choice A and E for that reason. These energy versus time graph cannot go beneath the t-axis because energy is a scalar. So that leaves me with choice C and D. Now, in order to pick the right choice between C and D, both of these graphs here start at 0. That's because at maximum amplitude, the object has not started oscillating yet. It hasn't started moving yet. So if you have no velocity or no speed, then KE must be 0. So both these graphs starts at 0 for KE, so I'll keep that condition. However, I think what differentiates between these two graphs is the time interval that's given. So here I made a note for you. If this is capital T, well, half of that midway would be just T over 2. So in this graph here, I filled this T over 2 out for you. Okay. Well, if you watch my cursor, at times equal to 0, the object hasn't moved yet, so its KE must be 0. But by the time it travels a fourth of the period, it reaches equilibrium, which is where V max is. Okay, so that's where kinetic energy is max. And then from x equal to 0, it goes all the way past that, and it goes to positive A, or A for amplitude. And it comes to a stop, and that would just take a half a period. Okay, so from negative A to positive A is a half period. So it's important that you understand that at positive A, it comes to a stop, and that time is half a period. So I would pick choice E for that condition. At half a period, the block comes to a stop again on the extreme far right, based on what I've given you. So therefore, KE has to equal to 0. If you look at D, D is saying that at times equal to half of a cycle, KE is max, which contradicts what actually physically happened. Half a period will require the object to come to a stop on the far right. If you're stopping, you don't have any KE. So this particular choice D falls apart for that particular reason. Okay. All right, let's do this one. This one here, you're given a velocity time graph, and it says here, this says the displacement of a particle has been measured so that it is 0 at times equal to 0. So here the object starts at rest, and it says point Q refers to a point in its motion. All right, so here you're given velocity time graph, and it says which of the following row is correct. So to help you visualize this, I'm just going to go ahead and give you a diagram here. Because it says initially starts at 0, and then all of a sudden you let it go, and the velocity is all positive, which implies that initially it got compressed. It got compressed and was held stationary, so therefore V is 0. But with the moment you let this particular diagram go, it'll shoot to the right to begin with, which makes sense based on the graph, because at times equal to 0, your velocity is 0. But as time progresses, to 5 seconds, you can see that the object starts to speed up and then eventually max out at equilibrium, and then from equilibrium it'll start to slow down again, which takes a half of a cycle. Okay, so I gave you a visual that kind of help you visualize this particular velocity time graph. So the box is initially compressed for this problem. Now let's do this one. You're essentially asked to find which row is correct. So here's the first one. It says time for maximum displacement. Well, maximum displacement occurs at extreme left and extreme right. So I'm just going to go ahead and point this out. At maximum displacement, the object must come to a stop in order for it to change direction. So I know at 5 seconds, the velocity graph crosses the t-axis. I know at 10 seconds, the velocity also crosses the t-axis, suggesting that these red points that I have on the slide here, that's where it comes to a stop. So therefore, it's either at extreme left or extreme right. Okay. So here as well, here's 15 seconds. So essentially, anytime your velocity time graph crosses t-axis, it comes to a stop. Okay. Now you're asked to find which row. So times for maximum displacement, well, it would have to be 5, 10, and 15, and 20. But I'm not going to go all the way up to 20 because the options here doesn't include 20. So for that reason, I'm going to go ahead and cross out choice A. Okay. Choice A said that the maximum displacement occurs at 2.5. No, thank you. These red dots suggest that the object comes to a stop at 5, 10, 15, and 20 seconds. 2.5 and 12.5 does not meet that condition. I'm also going to cross choice C out for that reason. I'll keep B and D because both these have 5 and 15 seconds, which matches with the red dots that I have. So it doesn't include 10, but it does include 5 and 15, okay? So the only thing that you need to differentiate here is the acceleration at point Q. Well, if you look here at point Q, this is the velocity time graph. The tangent line of a velocity time graph is your acceleration. Or you just need to know that when an object reaches maximum velocity, its acceleration is equal to 0 because it stops accelerating. So this is an essential point for you to hopefully keep in mind. V max occurs when A is equal to 0, right? Which again, logically makes sense because if A wasn't 0, then the object would continue speeding up or slowing down. So V max occurs when net force is equal to 0, which suggests when A is equal to 0. So if that's the case, as you can see here, V max occurs at this particular point Q. So I'm just going to say that the acceleration here is 0. So the only answer choice that matches this condition is choice D. Okay, because I'm looking for acceleration, and that is 0. Choice B that I kept for a bit says that the acceleration is 2, which is false. So I'm going to go ahead and highlight choice D, because at point Q the tangent line is 0. All right. Let's move on to this one. This one says that you have a object oscillating in harmonics from positive A to negative A, and then it says the graph here is a function of time, and it says that which of the label time, here's TA, TB, TC, TD, is there negative work done? So I want to highlight negative work. Negative work is when the force is acting against the object's motion. So in this case, you're looking for signals of when an object is slowing down. So here you have TA, TB, TC, and TD. I'm just going to go ahead and remind you that net work equals net force times displacement. However, you can break up net force into MA and times displacement. I like to compare A and X because A and X needs to be opposite in order for an object to slow down. So for example, if an object is going right, and if velocity is going right, for it to slow down, A has to be negative. Okay, so using the statement, in order to get work is negative, you need A to be negative and then X to be positive, because the only way to get a negative number is you have a negative and a positive. Here I'm going to leave out the mass because mass is a scalar, so I don't need to really focus on mass. A is a vector, displacement is a vector, so these are the only two things that have signs. So once again, in order for you to have a negative W, you need A to be negative, and then you need delta X to be positive. Or you can also get W to be negative if A is positive and then delta X is negative. Okay, so again, anytime A and delta X are opposite, I know the object is slowing down. It's just a matter of which way is it moving. All right, so to do that, I can also apply, the work kinetic energy theorem. So in order for you to get negative work, I just made a note here for you. I want to break up delta K into KE, or KF minus KI. And then for you to get a negative quantity, KF has to be smaller, because a small number subtract a big number gives you a negative number. Okay, so I'm just going to make a note for you. KF is small, and therefore if KF is small, the object has to be moving slow. And then Ki has to be big, but if Ki is big, then it's moving fast. So in order to get a negative number, you need a small number subtracted from a big number. All right, so now what gives us feature, which of these time location here gives us that feature? I would go with C, because at point C, all you have to do is look at the tangent line. This is an X versus time graph, so the tangent lines tells you whether an object is speeding up or slowing down. So at C, I noticed that the graph starts to taper off and it reaches 0. So therefore, I would pick time TC because the object is slowing down, which matches the conditions that I need. I need slow speed minus fast speed. Okay. All right. So the answer for here would just be C at point TC. All right, and that's it for this particular video. Stay nerdy, don't be whack.